Can absolute value inequalities solve optimization problems? Imagine trying to find the best way to minimize costs or maximize profits while keeping certain limits in mind. Sometimes, these limits involve distances or deviations, which is where absolute value inequalities come into play. They might seem tricky at first, but they are powerful tools for solving real-world problems. Absolute value represents how far a number is from zero on the number line, regardless of direction. For example, the absolute value of -3 is 3, and the absolute value of 5 is 5. When you see an inequality like the absolute value of a number is less than or equal to a certain value, it means the number is within a specific distance from zero. In optimization problems, absolute value inequalities often set boundaries or constraints. For example, if you want to keep the deviation of a measurement within a certain range, you can write an inequality like the absolute value of the difference between your measurement and the target is less than or equal to a limit. This helps define the feasible solutions for your problem. To work with these inequalities, you can split them into two linear inequalities. For example, if you have the inequality the absolute value of x is less than or equal to 5, it can be rewritten as two inequalities. X is less than or equal to 5, and is greater than or equal to -5. This makes the problem easier to handle because it turns a complex inequality into two simple linear inequalities. When absolute value inequalities involve greater than or less than signs, the solution becomes a bit more complicated. For example, the absolute value of x is greater than 3 means is either less than -3 or greater than 3. These create solution spaces that are not always straightforward, especially in optimization problems where you want to find the best solution within those limits. In some cases, the solution space might be non-convex, which means standard linear programming methods might not work directly. Advanced techniques like mixed integer linear programming can be used here. These methods introduce binary variables to handle the logical conditions created by absolute values, allowing you to find the optimal solution even in more complex scenarios. So, yes, absolute value inequalities can definitely help solve optimization problems. They are especially useful when you need to model constraints involving distances or deviations. By converting these inequalities into linear forms or using more advanced methods, you can find the best solutions that meet your limits. Understanding how to work with absolute value inequalities is a key step in mastering their role in optimization. Starting with simple inequalities and learning to rewrite them as two linear inequalities builds a foundation that makes tackling more complex problems easier. For example, minimizing the absolute deviation in data analysis or setting tolerance limits in engineering are practical applications of these concepts. This way, learners can see how algebra connects to real-world decision-making and problem-solving.